Hello friends, welcome to this next video on complex analysis. In the last video we have seen that whenever we have a complex valued function like this, okay, this is something like this, x u of x comma y plus iota times v of x comma y, and this function may or may not respect the complex structure of z. For example, the function z square respect the complex structure of z plus but f of z is equal to x. Okay, this does not respect the complex structure of z. So we call such functions as admissible functions and such functions as inadmissible functions, and we wanted to have a criteria that will tell us that which kind of functions are admissible and which kind of functions are non-admissible. And for that we have something called analyticity, okay, that we will study in this video. Analyticity tells us, this somehow gives us a criteria to distinguish between inadmissible and admissible functions. Okay, so before analyticity we will start with differentiability, and there is another reason to study differentiability. We have a complex function, we have studied its limits and limit and continuity, then obviously the next thing which we have to study is differentiability. So suppose we have a complex valued function, so it means that we have a function from a complex plane to a complex plane, right? We have a complex valued function of complex numbers, right? And at any point z0, and we want to know whether the function is differentiable or not, or we want to have what is the definition of differentiability at this particular point, right? So let us see that what do we mean by saying that a function is differentiable at this point z0. Extending the definition of real analysis, we have this thing that we define the derivative of z, f of z at the point z0, and we write it like this, is as limit of delta z tending to 0, right, f of z0 plus del z plus minus f of z0 divided by delta z. This is nothing but an extension of differentiability in case of real analysis, right? Now what here you have to notice that the delta z is a complex number, so it is a combination of delta x and delta y, right? The only thing is, in case of, let us draw the parallel analogy with real analysis. In case of real analysis we had something like this, limit del x tends to 0 at any point x0. The differentiability means we have to check this limit x0 plus del x minus f of x0 divided by del x, right? In this case, what was the situation, that we have this point x0, we can go from this way or this way, so delta x can go to 0 from left or right. That is why we used to check the left hand limit and the right hand limit in case of real analysis, and if these two limits are equal, then we say that the function is differentiable, because existence of limit means that you can come from any path, the limit should be same, right? And of course finite. But in this case, see, there are infinite number of ways to reach z0. Okay, I can reach z0 in infinite number of ways. I can come to z0 along straight lines from any side, I can come to z0 along a parabola or hyperbola or any arbitrary curve. So there are infinite number of ways to approach this z0. Okay, so that is a major difference. So you cannot do like this, that in that case we had only two directions and that two straight lines, so you can check the left hand limit and the right hand limit. So if the limits are equal, you say that the function is differentiable. So life was simple in case of real analysis, but that is not the situation here, because there are infinite number of paths. So it is impossible to compute the limit along every path and then see whether they are equal or not, right? So this is the major difference between complex analysis and real analysis, differentiability, right? So this is the definition. Okay, the only thing is that this limit should exist. Okay, so basically we say that a function at a point z0 is differentiable if this limit is existing, and here you have to note that this del z can go to 0 along an infinite number of ways. Now let us look at some examples. So first example I'll give you an example of non-differentiable function. I'll prove that f of z is equal to z bar, which means this is complex conjugate of z. We already had the definition of this. This is defined as x minus iota y, right? I'll prove that this is nowhere differentiable function. Okay, so let us see that. This is a nowhere differentiable function. Okay, so we have to look at this limit at any point z0. Let z0 be any complex number, and we want to check the limit of this function at this point z0. So we have to look at this thing, z0 plus del z minus f of z0 divided by del z, limit of this thing, right? Limit del z tending to 0. So what is this? This is equal to limit del z tending to 0, z0 plus del z bar minus z0 bar divided by del z. This is equal to limit del z tending to 0, z0 bar plus del z bar, because z1 plus z2 bar is z1 bar plus z2 bar minus z0 bar divided by del z. This and this cancels, right? So you are left with limit del z tending to 0, del z bar upon del z. Okay, now you have the following situation. You have this, your x-axis, you have your x-axis, and this is your y-axis, right? Here is your point z0, right? And you have to approach this point. Okay, so one way is that I am approaching this point along horizontal line, right? It means that my del z is actually del x. Okay, there is no vertical component, right? If I am coming along horizontal line, so one way is this limit should exist independent of the paths. So one way is if I am approaching horizontally, in that case I have del z is equal to del x. So what is the limit? Limit will be limit del x tending to 0, del x bar divided by del x. Del x bar is nothing but del x because it is real, so this is 1, so limit is 1, right? Now there is another path, another way which I can use. I can come to z0 along vertical line. Along vertical line there is no horizontal component, so here my del z is iota del y, right? So if I am coming from, I am approaching z0 vertically. If I am approaching z0 vertically, then what is the situation? I have this limit iota del y tending to 0, iota del y bar divided by iota del y, right? Now what is this? This is equal to conjugate of this thing is minus iota del y upon iota del y, so this is minus 1, so limit is minus 1. So it means that if I am coming to z0 along this horizontal line, the limit is 1, and if I am coming from vertical line, the limit is minus 1. It means that limit is path dependent. It means that limit does not exist, right? It means that this function f of z is equal to z bar is nowhere differentiable function. And you must remember that we have seen that this is a culprit function for admissible functions. We have seen that whenever z bar will appear, that function will be inadmissible. Okay, so there is some connection, and this function is also nowhere differentiable function, and I am saying that there will be a connection between analyticity and differentiability. Okay, so that we will see later. For now we should know what is differentiability. We should understand the definition of differentiability, right? So most of the times in complex analysis we just look at the cases where the function is not differentiable, because it is easy to establish the non-differentiability, okay, in case of complex functions rather than differentiability, because in case of real lines we can establish the differentiability by looking at the left hand limit and right hand limit, okay, but that thing we cannot do here because there are infinite number of paths. So what we have to do, we have to rely on the definition of epsilon delta. Okay, you must remember that for differentiability we have epsilon delta definitions. We will go to those things later, right? For now we should know what is differentiability. That's it, right? So we have an example of a function which is nowhere differentiable. Now let us look at some properties of differentiability, right? These are similar properties which we have in case of real analysis, right? The first property is okay, we have just proved that f of z, first property is f of z is equal to z bar is nowhere differentiable, right? Similarly, you can prove that f of z is equal to real of z, f of z is equal to imaginary of z, f of z is equal to mod of z. All these functions are nowhere differentiable functions. Okay, and we have seen that all these functions were culprit for the admissible functions. Okay, these are nowhere differentiable functions. This you can easily prove in the way similar to how I have proved that z bar is nowhere differentiable function, right? And the second thing is suppose I have a function which is z raised to power n, right? We know that derivative of x raised to power n is n x raised to power n minus 1. Similarly here we can prove that derivative of z raised to power n is n into z raised to power n minus 1. Okay, I'll not prove it here, this is simple to prove, you can do it. Then we have similar properties that if f and g are differentiable, then their sum and subtraction is differentiable at that point. Okay, so this is the differentiable of sum, or the difference is the sum or difference of the derivatives, single derivatives, right? And the next thing is, if you multiply a differentiable function with a constant, okay, it will still remain differentiable, and this is a relation. And then there is a product rule similar to what we have in case of real analysis. If you have two differentiable function f and g at a point z, then their product is differentiable at that point, and the derivative is given by f dash z g of z plus g dash z into f of z, right? Then we have quotient rule. Okay, if f and g are differentiable at a point z and g of z is non-zero, then their quotient is differentiable at that point, and the derivative is given by the similar rule g z square, okay, g of z into f dash z minus f of z into g dash z, right? And then we have differentiability of the composition of the function. Suppose we have a function g which is differentiable at z, okay, and f which is differentiable at f of g of z, then f of g, okay, which is f of g of z is differentiable at z, okay, and we have the chain rule. The derivative of f of g of z is what? It is f dash at zz into g dash z. So this is chain rule. So we have what? We have product rule here, we have quotient rule, and we have chain rule. Okay, so we have similar rules to what we have in case of real analysis, right? So we can just apply these rules to just compute the derivative, just to have a flavor. You have a function f of z is equal to z square minus 1 upon z square plus 1 whole raised to power 100. You have to find the derivative of this function. You can simply do f dash z. This is we will apply chain rule. Obviously this is differentiable function whenever z is not equal to plus minus iota. So we are discussing the we are taking the values of z except plus minus iota. So what is f dash z? It is 100 into z square minus 1 upon z square plus 1 raised to power 99 into the derivative of this thing, and here you will apply the quotient rule. So derivative will be z square plus 1 whole square into z square plus 1 into 2z minus z square minus 1 into 2z, right? So you can just compute this thing. It will be 400z into z square minus 1 raised to power 99 upon z square plus 1 raised to power 101. You can check, yeah, it will be 101, 99 from here, 2 from here. Okay, so this is your final answer, right? So these are some of the properties of differentiable functions. Now let us look at one more example. Look at this example. F of z is equal to mod z square, right? We can prove that this function is differentiable only at z is equal to 0 and nowhere else. Okay, it means that we have a function from complex plane to complex plane, and this particular function is differentiable only at this point, and at every other point this is a non-differentiable function. Okay, so this is pretty simple to prove. You can just you have to look at this limit f of z naught plus del z minus f of z naught upon del z. What will be this? This will be z naught plus del z modulus square minus z naught modulus square divided by del z Now you can write, you have this property that modulus of z square is z into z conjugate. So I can write this thing as z naught plus del z into z naught plus del z bar minus this is z naught bar divided by del z. So what is this? This is equal to, you can just write it as z naught plus del z into z1 plus z2 bar is z naught bar plus z2 bar minus z naught bar divided by del z. Now you can multiply this thing, and what you finally get is this will z naught bar will cancel, and you will have z naught bar plus del z bar plus z naught into del z bar upon del z, right? So we have the following situation. You have the following situation that f of z naught plus del z minus f of z naught divided by del z is equal to z naught bar plus del z bar plus z naught into del z bar upon del z, right? Now if we are checking the differentiability at z naught is equal to 0, if z naught is 0, then what is this thing? This quantity is, in that case, is equal to, you have this is 0, so this is z naught bar and this is 0, right? And we have to look at the limit of this quantity, limit del z tending to 0. What is this? This is 0, right? You can come along any path, this limit will be 0, right? So in this case, when z naught is 0, the limit is existing, therefore function is differentiable at 0, okay? When z naught is non-zero, what is this? The limit will be limit of this thing plus limit of this thing, del z tending to 0, del z tending to 0 plus z naught of into limit of del z tending to 0, z naught bar upon z del z. Now this thing is independent of del z, therefore the limit is z naught, the limit of this thing is 0, and we have proved that limit of this thing does not exist, right? We have proved it in the last example. We have proved that z bar is non-differentiable. There we have proved that this limit does not exist, right? It means that whenever z naught is non-zero, this function is function which is f of z is equal to modulus of z square is nowhere differentiable, is not differentiable. It means that this function is differentiable only at 0, okay? It is differentiable, and elsewhere it is non-differentiable, right? So it means that we can have functions which are non-differentiable everywhere except at finite number of points, right? We used to have such functions in case of real analysis also, right? But most of the theorems of real analysis, but similarly most of the theorems for the complex analysis will work if your function is differentiable at least on an open interval in case of real analysis, and at least on an open set in case of complex analysis. So we want to look at the functions which are at least differentiable in an open set, not at a single point. We don't want functions which are differentiable at isolated single points, right? But we want to have functions which are at least differentiable in an open set, because most of the theorems which we will prove, they will be applicable if your functions are if your function is differentiable at least in an open set, okay? So for that we further define something called analyticity, right? What is analyticity? Let us look at that. First I'll define what is analyticity. Just write the definition. A complex valued function f of z is said to be analytic on an open set G, is said to be analytic on an open set G if it is differentiable at every point of G, okay? It means what? You have an open set G, you say that a function is differentiable in this open set if it is differentiable, sorry, you will say that a function f is analytic on this open set G if it is differentiable everywhere. right? Now you have to note this thing that analyticity is defined for sets defined on open sets, whereas differentiability is defined at a point. Right? It means that analyticity is a set property, right? So basically you have to define it for a set, and differentiability is a point property, right? You can define it at a point. But you must have heard many times that we say that f of z is analytic at z naught, right? What does that mean, right? Right now we have defined analyticity for an open set, not at a point. So the meaning of this thing is, we say that a function is analytic at a point z naught if it is analytic in a neighborhood of z naught. In a neighborhood of z naught. Neighborhood means open set around z naught, right? So if we have a situation that we have a point z naught, and around z naught we have an open set which is a neighborhood of z naught, and if function is differentiable everywhere on this open set, then we say that our function is analytic at that point, right? So we have analyticity defined for a point in this sense, right? Okay, so later on we will see that this analyticity gives us a tool, to distinguish between admissible and non-admissible functions. Okay, we will see this in the course. You must remember that I have told you that admissible functions, in case of non-admissible functions, z, real of z or imaginary of z or z bar will appear, right? And if a function is free from these things, then that function is admissible, right? But it was difficult to see whether the function is free from these things or not, these three things or not, right? Later on we will see that an analytic function can always be written only in terms of z. Okay, if a function is analytic, then it can be written only in terms of z. These three things, z, real of z, imaginary of z, and z bar, will not appear in the representation of fz if fz is analytic. So in this way it will tell us, it will give us a tool to distinguish between. So we will come to know that whenever a function is analytic, it means that that function is admissible. It means that we will see that admissible functions are analytic functions are admissible functions. It means that analytic functions respect the complex structure of z, right? Okay, now what will be our next video plan? So right now we have come to know that we have defined differentiability, we have defined analyticity, right? And we know that this thing will give us a tool to distinguish between admissible and inadmissible functions. Okay, that is a job which we will do later on. Right now we have seen that we have given a definition of differentiability, that this limit f of z naught plus del z minus f of z naught upon del z should exist, right? And in case of real analysis, this limit exists or not, it is easy to check. You have left hand limit and right hand limit. But in case of complex analysis, to check whether this limit exists or not is difficult. Okay, therefore we look for another tools, right, to check whether a function is analytic at a point or not. What do you mean by saying that a function is analytic at a point? It means that it is a differentiable function in a neighborhood of that point, right? It is differentiable function at every point in the neighborhood of that point, right? So in the next video we will try to have another tools, okay, another than this definition of limit, to check whether a function is differentiable at a particular point or not. And it turns out that that tool is Cauchy-Riemann equations. Okay, CR equations, you must have heard about these equations, Cauchy-Riemann equations. That is our task in the next video. Thank you.